So we're going to revisit Fermat's principle, and this time we're going to show how Snell's law comes out of Fermat's principle and gives us refraction. So just kind of a quick reminder, Fermat essentially states that the light traveling between any 2 points is going to take the path that minimizes that travel time. Obviously, it has to involve the interface in question. I should point out again, this is not explaining why this happens, but it's just a principle that does show the angle of incidence equal angle of reflection for reflection, and it does show Snell's law falls out of this. So let's take a look at a situation where we have some refraction, and then we're going to end up showing that Snell's law is a direct result of that. So we have here a medium, and in the upper medium, the light is incident from up above, heading down, and in that medium, we have index of refraction n1 and velocity v1. In the other medium, we have index of refraction n2 and velocity v2. And so with these dimensions set up, we're going to calculate the time it takes the light to travel from point A to point B. So this first term in my equation for time is how long it takes to go from point A to the interface. This second term then is how long it takes to go from the interface down to point B. And so then making use of the Pythagorean theorem, I can rewrite L1 here, and then this is L2. And then I need to minimize the time taken, and so I'm going to take the derivative of t with respect to this quantity x. In other words, I'm considering any of the possible paths this light might take. It could have taken that path right there, in which case my value of x would have been there. So taking that derivative, here is what I get. It's very similar to what we got for the reflection case. The primary difference is we now have this v1 and v2 that get involved because the velocities are different in the two media. We're going to go ahead and make use of the fact that I can rewrite this term right here as the sine of theta 1. This term right here is sine theta 2, and so that I can plug these in to my equation for dt by dx. And what we get is this thing right here. Let's go ahead and solve that. And then I'm going to go ahead and make use of the fact that n1 is c divided by v1, n2 is c divided by v2. And so if I plug that in, basically I'm multiplying both sides of this equation by c, and then replacing c over v with n. We end up with Snell's law. One thing that's kind of interesting is that this equation does show that theta and v are sort of inverse related to one another. In other words, a slower, smaller v does indicate a larger angle. And so that's maybe a good way to remember how the light should bend.